Electric field due to a uniform surface charged disk. Objective: to derive the electric field due to a uniformly charged disk. Consider a circular disk of radius a. Charge is uniformly distributed over one of its surfaces. Areal charge density, that is, charge per unit area of the disk, is given as sigma. Let's calculate the electric field due to this planar charge distribution on the axis of the disk. Let P be a point on the axis at a distance x from the center O. The disk can be assumed to be a collection of several concentric rings of infinitesimally small thickness. Consider one such ring element with charge dq, radius r, and thickness dr. If the periphery of the disk subtends an angle theta at P and the ring subtends an angle alpha at P, from the right-angled triangle, tan alpha is equal to r by x, therefore r is equal to x tan alpha. On differentiating the equation, we get dr is equal to x secant square alpha d alpha. Area of the ring element is the product of its circumference and width. As the charge is uniformly distributed, charge on the ring element is the product of charge density and area of the ring. Upon substituting the expressions for r and dr, we get dq is equal to sigma 2 pi x square tan alpha secant square alpha d alpha. The distance between any point on the ring and P is root over r square plus x square, and cos alpha is equal to x by z. Therefore, z is equal to x secant alpha. From the discussion on electric field due to a ring, we know that the magnitude of the electric field at a point P due to this elemental ring is k dq by z square cos alpha, and it is away from the center. On substituting k with 1 by 4 pi epsilon naught and the expressions for dq and z, we get dE is equal to sigma by 2 epsilon naught sine alpha d alpha. The electric field due to all such ring elements will add up, and magnitude of electric field due to the complete disk is given by integral of dE from 0 to theta. E is equal to integral of sigma by 2 epsilon naught sine alpha d alpha from 0 to theta. Taking the constant terms out of the integral, on integration and substitution of the limits, we get E is equal to sigma by 2 epsilon naught 1 minus cos theta. From this triangle, cos theta is equal to x by root over a square plus x square. Therefore, the electric field along the axis of a uniformly charged disk is given by sigma by 2 epsilon naught into 1 minus x by root over a square plus x square. This result can be used to determine the electric field produced by a non-conducting infinite sheet of uniform charge distribution on one of its sides. In this case, radius of the disk tends to infinity. The second term in the bracket tends to 0, thus electric field near the non-conducting infinite sheet is equal to sigma by 2 epsilon naught. For a point very close to a finitely charged disk, x tends to 0, giving us the same result, sigma by 2 epsilon naught. Summary: the electric field due to a uniformly charged disk at a distance x from the center along its axis is sigma by 2 epsilon naught, 1 minus x by square root a square plus x square, and it is directed away from the center. Electric field near a non-conducting infinite sheet of uniform charge distribution is sigma by 2 epsilon naught.